Hello everyone, welcome to this tutorial on PyTorch and deep learning, where we try to understand some fundamental concepts associated with training a neural network and how we can do that using a framework like PyTorch. So before we go into the specific implementation of neural networks, let's try to understand certain concepts that are associated with neural networks. So neural networks are typically these black box techniques where you have certain number of input variables coming into the network, let's say x1 till xn, and the model is trying to output something. Let's for sake of simplicity, let's say that we are training a classification algorithm and it is making a prediction y hat depending on these x's. Your data set would, if it's a supervised classification problem, as we said, so it would consist a set of x and y's, where x's are your input variables and y's are the class values for that particular sample, and there could be n samples in your whole data set. So while you have your input x's, you also have the associated label for that sample, and y hat is the model prediction. So if you compare the model prediction y hat with let's say the actual goal truth that was coming from your data set, let's just call it y, and you compare these two, and you can quantify how similar or dissimilar are these two values, right? Similar would mean that your prediction, that the model prediction is same as your goal truth. Dissimilar would mean that whatever the prediction that the model made is actually does not match with the goal truth or the annotation that is there in your data set, right? And this comparison, which essentially quantifies the similarity or dissimilarity between the prediction and the given goal truth, is what we call loss. So if we look deeper into a neural network, as we said, there are some input values that are coming in. There are layers of neural networks, one followed by other, and you have, let's say, after that you have a final prediction y hat, the final output. Let's say the final output, let's say this is y hat, and you from your x1, from your data set, you also have the goal truth. Let's call it gt, or gt is a good variable name, and you can compare loss function would compare the model prediction and gt. And these intermediate layers of neural network are also weights. Let's call them w, w1, w2, or w11, w12, w13, so on till w1n. And there could be various layers associated in a neural network. So this could be layer 2, and this could be layer 3, and again they would have some number of weights within this network. In a simplest case, in a fully connected neural network, each variable is connected to every other unit. So this and so on, and I mean this same connection would follow throughout the network. W1 would be connected to this weight, this would also be connected to this weight, and so on and so forth, right? Every component is connected to every other component, and there are these series of connections throughout the neural network which enable the neural network to make this prediction. So when we start out, let's say that you're just starting the training of this particular neural network. What are the values of these weights? X's are given, right? And the model has to predict some y hat. So when you start out, all these weights that are there in these layers, let's say these are layers. This is also called depth of the neural network, and this is also, let's say, breadth of the neural network, of breadth of each layer, let's say. And again, these are again some hyperparameters, so what is a good combination of depth or breadth is you have to understand like what combination of it is good for your solution and good for your problem. So if all the weights are connected to all the weights, when you initially start training out, how are these weights, what are the values of these weights? Are these sets of zeros? All the weights start with 0 values, or all the weights are ones, or all the values are somewhere between 0 and 1 randomly initialized? Right? Let's assume this case where all the weights are randomly initialized between 0 and 1. So this is called a forward pass, where your x1s, the input samples x1 to xn, all the input variables pass through the network till a model makes a final output, or makes a final prediction. Now the model made the final prediction, you compare it with the actual goal truth, and you come up with this quantification of how similar or dissimilar are these prediction and goal truth. Now it's intuitive that depending on how big or small this loss is, you have to adjust these parameters in your whole network, right? Let's all these w's, all these weights, you have to adjust them in your network so that your model gets better at this job. Gets better at this job of predicting an output. How do you do that? So the idea is that depending on loss, we have to adjust all the weights in the network. But how do you adjust that? How do you adjust loss? Based on loss, how do you adjust these parameters, right? So one concept here that makes it easy to train the network is this concept of gradient, right? So think of a group project that you're doing as part of your course, and there are 4 people, A, B, C, and D, that are in a course, and the final marks that are associated given to that project are, let's say, M marks are given, and you have to distribute across these 4 project members depending on some criteria. Right? So one criteria that you could use is that how much did this student A contribute to this project? How much did student B contribute to the project? How much did C contribute? And similarly, how much did D contribute? So we apply the same analogy to this to the training of these networks as well. We see that all these weights when we start out are randomly initialized, and these weights are playing some role in making this final prediction, right? So if these weights are playing a role in this final prediction, and prediction has some loss associated with it, it's logical that in this loss each of these weights had certain role to play. Now how much is that role? Like, how do you quantify that role? How do you quantify what was the role of this particular weight in this final loss, or this particular weight in this final loss, right? And that is the concept of gradient, right? So gradient are, let's say, you have a function which is y is f of x, right? So if you do simple differentiation dx, you get some value, right? So what is this differentiation telling you? This differentiation is telling you how is y changing with respect to x, right? And that is what we wanted, right? How is loss changing with respect to, let's say, wi. Now this was a very simple case where y was dependent only on one variable called x. But in this complex network, you can see that loss is dependent on multitude of these weights, right? So y is not just dependent on one single x, but it's slightly complicated. Let's say think of a hypothetical situation where y is dependent only x1 and only 2 variables, x1 and x2. So how do you now translate this notion of rate of change? Dy by dx was telling you how is y changing with respect to x. where it was only a single variable. Now you have two variables, there are two independent variables, y is a function of both of them. So now you have to understand how is y changing with respect to x1 and how is y changing with respect to x2. That's where partial differentiation comes into picture. So partial differentiation would tell you how much is x1 changing with respect to y, how is x2 changing with respect to y is changing with respect to x2. Partial differentiation, these are dou y by dou x1 and dou y by dou x2. So if you have a nested function like this, what you can do in turn is that you can apply chain rule and find out the gradients in a nested manner, right? And the same case applies in this case of neural networks as well, because you have nested functions here as well, because you are going layer after layer, and you can come back and say that for me to compute the gradients of this, I'll compute the gradients of this first, then based on that I'll compute the gradients of this, based on that I'll compute the gradient of this, and this would be multiplication of all these three, right? And that is what is called backprop, right? So in first step, what did you do? You computed a forward pass, you did a forward pass and you made some prediction, you compared the prediction with the actual goal truth, you computed some loss, and now you're trying to understand what is the contribution of each of these weights dependent on this loss, right? So, and backprop and chain rule and partial differentiation allows you to backprop is a combination, let's say, gradient calculation and chain rule of these partial differentiations, right? So based on this, you can basically compute how much did all of these weights in your network, let's say there are n weights in your network, right? All of these how did all of these weights how much did they contribute to this final loss, right? So intuitively it makes sense that if this is a high value, that means that this weight 1 contributed a lot to this loss, right? It had a huge role in increasing that loss. That means that you have to adjust that weight by a lot, right? So let's call it an updated weight or updated weight. This would be W1 minus the same loss, right? Depending on the loss, you would adjust your weights. W1 had a certain influence on the loss, and whatever is that quantification of that influence, I am adjusting my initial weight with that loss, right? So this would be now my updated weight, and the same would be the case for any weight in your network, right? Wn minus dou L by dou W1. Typically, you also add something called eta. Eta is called learning rate. Where basically you are adding some weighing factor to this loss. So now that you have figured out a way to adjust your network parameters, you can do this training again and again over whatever number of samples are there in your data set, and that's how you train a neural network, right? You are iterating in your training procedure. This is what are the basic components. You start with a sample, you pass the sample through the network, that's called a forward loop. Your model makes some prediction y hat, you compare that prediction with the goal truth, and that quantifies your loss. Now using gradients and backprop, what you're trying to do is you're trying to understand how much of these each weight, how much did they contribute to the loss, and depending on that you adjust your network weights using this formula, right? This is what is called gradient descent. So one simple analogy would be like this. Let's say that take a very simple case where loss is dependent only on this x variable, right? There is only one x in your whole function, and loss is only dependent on that x. And let's say that there is a loss increases or decreases based on, this is how loss is related to x based on this line. So what you're trying to do is that you want to decrease loss as much as possible, right? If your prediction was good, the loss would be very less. If the model prediction was bad, the loss was high. So what you're trying to do is that you want, the whole point of your training your neural network is to reduce this loss as much as possible, right? So if this is the loss curve, you want to iteratively come lower and lower till you reach the global minimum. Okay. So at any point you're trying to understand what is the slope, and you're taking a direction in that slope, right? Slope, gradient are the same thing. Right. So depending on what is the slope of slope between L and X, you take a direction in that slope. And if this is your loss curve, you're trying to take steps incrementally as you're training your neural net, so that you end up at a global minimum. You don't want anywhere there, or you want basically an optimal solution where your loss is as minimum as possible, right? For that you have all the data samples that are there, and you have some neural architecture for it, and you have some way of computing the loss. If the model makes a prediction, you are comparing y hat and y and computing loss. And the whole point of your neural network training paradigm would be to reduce this loss as much as possible. Now this is a very simple example where I'm saying that loss is depending on only one x, right? If you look at this network, there are the number of weights in this network are, let's say, much more than one, right? So your loss curves aren't as trivial as this. They could be very complicated. One complication could be like this, where your loss curve, right, is as complicated as this and not really a smooth convex like this function. So there are certain local minimas. This is also a minima, but in this locality, but there are global minimas here, right? So the point of training your neural network should always be to reach this global minima and never get stuck at this local minima, right? Again, these are called loss curves, or let's say cost functions, loss functions, essentially the same thing. All right. So here we had also looked that we are adding some weighing factor eta. We are not simply saying W1 minus dou L by dou W1. We are saying instead we'll weigh it by certain factor called eta, also known as learning rate. So learning rate, what it does is that it modulates how small or big a step are you taking. If eta is very large, what you're doing here is that you're taking bigger steps. You started here, you take a big step and you end up here. You take another big step, you end up here. If the eta is very, very small, you're saying that instead of taking a larger step, you take a smaller step, right? So by controlling eta, what you're controlling is the number of steps, amount of steps that the quantum of the step that the model is taking, and it should not be too large. It should not take such a large step that it ends up here, right? And it should not also take very, very, very infinitely small steps. The problem with taking very large steps is this: you end up doing this, right? You keep oscillating between very high values of losses, and taking very small steps is that you will reach this final endpoint very, very, very slowly, right? So again, eta is a hyperparameter. There is no one value for eta. You will have to adjust it based on your network and how it's behaving. It's a hyperparameter, right? So one way to visualize this is something called TensorFlow Playground, where all of these concepts could be visualized to give you a better understanding of how they function. So let's say that we are doing some classification problem, and there are different classes of problems, right? So let's just stick to these two, right? So here, this is a very simple classification algorithm. If the network manages to learn this one decision boundary, which is a simple line, the model is good at classification. Whereas here it is a bit complex because the model has to learn a circle, which is slightly more complicated than a simple line, right? And in this, these are your input variables x1 and x2. These are the two x's that are there in your data, and the color is indicating what is the class of that particular sample. Right? And there are certain other parameters associated with it, where you're saying that the learning rate could be varied across multiple things. You have some activations or non-activation functions which are introducing some non-linearity and some other parameters, and the problem that we are doing is a classification problem. So by changing these neural architectures, you can add as many layers as you want. You can increase the depth of a particular layer. Instead of just relying on x1 and x2, you can say that I will rely on a combination of them, x1 square or x2 square, or x1 multiplied by x2, or I'll also, instead of just taking plain x1, I'll say sinusoidal of x1 and sinusoidal of x2, right? So this is where you can engineer your features. So instead of just taking those plain features, you are computing some variations of those input variables to understand if they can help you do a better classification. Yeah. And once you start on this play button, the network will start training. Right? So let's just click on that. You can say that, let's just pause here. You can say here that the color here, the color of the background, that is indicating if I give a new sample, some x1 and x2 values, and it falls in this yellow region, it will be classified it as yellow. If it falls in this blue region, that sample would be classified as blue, right? But looking at this class, it's doing a very good job of differentiating these yellow samples from the blue samples, right? And this plot is essentially telling you how training loss or test loss are behaving as the network training goes on. So if you, let's say, the previous case we had taken 0.03 as the learning rate. If you take a very small learning rate, right, you refresh it, you can see that it is learning slowly, right, as compared to 0.3, where you click off a button, it was already there. You can see here that the loss is decreasing much more slowly, and the decision boundaries are coming up a lot more slowly, right? So that's how learning rate would impact how your model trains. You don't want a very large value, you also don't want a very small value, you want an optimal middle ground. You can see that the decision boundaries are becoming more and more clear as the network keeps on learning. Right. So let's go back to 0.3 and let's take a much more complex problem. Right. Let's say that there are no non-linearities. There are no non-linearities. You are only taking x1 and x2. There are no more linear non-linearities put into the network. Right. Let's try to understand what a non-linearity is. So what we were saying here is that in this neural architecture, all the x1s are feed into the first layer, and every weight in this first layer is connected to every other weight in the second layer, right? So what is the what do we mean by, let's say, x1 till xn is going into the first layer? This is a layer 1, and there are some weights here. Right? What do we mean? What happens internally? What do we mean when we say that x1 is passed through this particular layer? Usually it is represented by some, let's say there is a weight matrix, and you are multiplying by x. X is again this vector representation of this, and you are applying some, and this is what a linear layer does. Right? Usually there is a linear layer which takes some input, does some linear operation, it multiplies by the internal weight matrix, adds some bias values to it, and that becomes the output of this particular layer, right? In comes x, out comes output of this particular layer. And what is happening internally in this, let's say if this was a linear layer, this is what would be happening. There are many other kinds of layers in neural networks. Let's just park that for now, but assuming that if it is just a linear layer, this is what is happening inside it, right? It is applying some matrix multiplication and it is producing some outputs. Let's say that this was a set of y1 till yn something, right? So what non-linearity does is that it applies some non-linearity on this particular output. Right. So what non-linearity allow a model to learn are these non-linear decision boundaries, much more complexer functions, right? As compared to this, where all the model had to run was a simple line, here the model has to learn a very complex decision boundary, right? And this is how non-linearities will allow a model to learn more complex decision boundaries in the network, right? And one way to introduce those non-linearity is this. Another way that you can improve the model performance to allow it to learn nonlinear decision boundaries is by complicating your input feature space, right? You give it higher order or a different mapping of those input variables, and they will also allow you to learn a more decision boundaries, right? And you can see that these are the activations that the model can see based on whatever input is flowing. And this variable, the activation, is just that, right? What is this non-linearity that is being applied to this output, right? So instead of so let's say this was y. So if it is just a linear layer, y would be, let's say, something like this. If you are applying some nonlinearity, it would be, let's say, sigmoid, some nonlinear function, in this case a sigmoid, applied on this particular matrix. Right? That's what we mean by applying nonlinearity in a neural network. When the activation is linear, we are saying that there is no nonlinearity. It is just simple matrix linear matrix multiplication like this. And when you can choose any of these activation functions, and they would end up applying some non-linearity to the network. And yeah, so let's just write this. So we are looking at a second example where the distribution of data is something like this. We are not introducing any non-linearity. The inputs are still x1 and x2, and there are no non-linearities in the whole network. And if I train this, you can see that all these decision boundaries, although the color gradation is still linear, there are no non-linearities coming here, right? So let's reset it. Try to apply some non-linearity and see what happens, right? So this example should tell you what is the outcome of putting up a non-linearity in the whole neural network. All right. So this was some theory and some visual understanding of how neural networks would train, right?